Kolkata. Should I introduce myself again? Hi, I'm Souvik. I am working at CC Kolkata with Dibyendu Nandi, and let me stop my video to save the bandwidth. Wait, yeah. So now the thing was, I asked ChatGPT and Google Bard to give me a quirky name for my slides. I gave it a description, and this is what came out of Google Bard. If it's really nice, the blame goes to me. If it is really cliche, the credit goes to ChatGPT and Google Bard. So let's move forward. I'll just spend a few seconds here. What you are looking at is basically a animation of how Earth's magnetosphere is evolving. There's no interaction. This is just a basic tool. Now, in this particular case, if you can see my laser pointer, this is sun. The sun-earth line is constant. So you're basically sitting static on the sun-earth line, and Earth's magnetic field is rotating based on the Earth's rotation about its axis. You can see the moon also rotating around the Earth. Now, there's a fundamental mistake in this animation. I'll come to that at the very end of this talk. Meanwhile, if you can find it, keep it within you. I'll come back to this. So let's start the presentation. The first question, very basic. Why do you need to study the sun? So I want the answer from you. You don't have to shout. You keep the answer within you. So I'll give you 5 seconds. Why do you need to study the sun? Okay. So by now you have an answer. And when I ask the same question to my colleagues and friends, I get two kind of answers. One is driven by our fundamental curiosity that we want to study plasma dynamics or MHD. We want to study nuclear physics or particle physics, or we want to study stellar evolution. So sun is the brightest object and the nearest star we have, we study sun, and so on. The other group is driven by the solar impact on our life. So to study star-planet interactions, to study space weather, which is basically a subset of star-planet interaction, to study planetary dynamics and use that to understand the exoplanetary dynamics and so on. Now, whatever you thought when I asked you to, why do you need to study the sun? Do you think that your answer actually sets upon either of these two, or maybe a subset of these two? Yep. So today, what I'm going to do is I'm going to talk about these 3 points on your right-hand side. So I'll start with why we need to study and the star-planet interaction, why you need to study and the space weather, why you need to study sun to understand planetary and exoplanetary dynamics. So whatever I'm going to talk about is now from sun to the planet. So let's start with to study the star-planet interaction. This is a nice artistic impression made by Chitradeep. Chitradeep is a colleague. Chitradeep is my colleague at CESI. So to understand star-planet interaction, the first thing we need is to know what is solar wind. Now, after Pratik's talk, I don't think I need to explain solar wind to you again. I don't want to bore you. Just to make sure that we all are on the same boat. If you look at on the right-hand side picture, the right side picture, so in solar, if you come from sun, we have core, then radiation zone, then convection zone, then photosphere, chromosphere, transition zone, lower corona, and upper corona. So if you plot the density and temperature, you see that in the coronal region, the density is low, the temperature is high, which tells us that it will have a huge thermal energy, but the gravitational attraction will be very lesser. And if you just intuitively think about this, that this is a fluid medium which is gravitationally less attracted and has a huge thermal energy, it will expand, and it expands as solar wind. This is a typical solar wind structure. Again, you have seen this, already seen this in Pratik's talk. So this we call Sparker spiral. This is an illustrative image. And when the solar wind comes near Earth, we'll first talk about Earth because we know Earth very well, more than any other planet. So when solar wind reaches Earth, it usually shows a density about 3 to 5 protons per cc, a velocity of 350 to 400 kilometer per second, a temperature of around 150 Kelvin, so which means that it's mainly plasma, a magnetic field because the solar wind also drives sun's magnetic field with it, around 2 to 4 nanotesla. Now, when this magnetized plasma interacts with our nearly dipolar magnetic field of Earth, what we see is this. At this moment, you are seeing the dipolar magnetic field of Earth, and here the solar wind comes. Okay. Now, this is not a real image. No spacecraft has taken it. This is typically a result of computer simulation. And I'm going to describe how we do this computer simulation. So to start with, what we do is in one line, magnetohydrodynamic modeling framework. So what is that? This is the typical MHD or magnetohydrodynamic equation. Again, I'm not going to bore you with equations. The first one is basically conservation of density. The second one is conservation of momentum. The third one is conservation of energy. And the last one dictates how the magnetic field is going to evolve with time. This is the very basic equations of MHD, where, so how many of you, so I can see you, raise hand if you know what MHD is. None of you know what is MHD? A few. Oh, nearly 50-50. So I'll just take a moment here because I have seen the schedule, but Yuhavda will talk about MHD maybe tomorrow. So just give you an overview. MHD is, let's say you have plasma, where plasmas are ion, but when you are seeing plasma from a length scale, where you don't actually bother about its particle definition, rather the whole plasma become a fluid to you, a fluid like air, a fluid like water. So since it's a fluid to you, it follows Bernoulli's principle. Basically, in a better way, Navier-Stokes equation, it follows conservation of density. But since it's a plasma, which is basically a club of ions or a set of ions instead of neutral particles, it will have a magnetic definition also. So it will interact magnetically. That's why you have the fourth equation, the induction equation, which dictates how the plasma will evolve with magnetic field. So all four dictates how the plasma will evolve as a hydrodynamically and magnetically. So in collaboration, magnetohydrodynamics. And to achieve this modeling framework, like Pratik, we are also using Pluto, because Pluto is a really nice code that solves MHD, this four coupled equation in all three dimensions. Now, we called our module, we have to name it, like Swasti, we have to name it. So we called it SESI Star Planet Interaction Module, in short, SPIN, SPIN, SPIN. And if you really want to picturize what are we doing, this is the video. So the sun is far apart from Earth. We are not at all bothered about the star, as I told you. We take a computational box near the planet, and within the planet, the solar wind moves along the planet to give us an idea how solar wind interacts with the Earth's magnetosphere. And to do that, we get solar wind data from L1 point. We currently have Discover, ACE, Wind. We will have Aditya there. So we get the solar wind data from L1. We create a computational domain, which is basically focused on the planet. We call it a far out system. And then from the boundary, the solar wind enters and interacts with the Earth's magnetosphere. Now let's talk about why we don't want to don't put the star here. Like, if you can see the yellow line at the, is someone asking a question? No, it's fine. So if you see the yellow line at the very bottom, if this represents 1 AU, that is the distance between sun and earth, and the sun is at your left, the earth is at your right, then this particular arrow represents L1 point. So L1 point is basically 1% of 1 AU from earth. So see, we don't have to now, if we really want to take this whole length scale into computational domain and then try to understand what's happening at your planet, it will be really difficult, because this huge length scale, you cannot resolve the earth. That's why it's better if you really focus on the near planet scenario. And since earth is very far away from the star, whatever is happening on earth is influenced by the sun, but whatever happening on sun, earth has no say to it. Now let's take the realistic scenario. On your left, you can see the actual computational domain. And in this domain, we have a earth. So this black dot, it's not a dust on your projector screen, it is the earth. And this is how it looks like. So it is resolved with 0.3 RE. So RE being 6,400 kilometer, it is resolved with around 2,000 kilometer grid, and which increases as you go from Earth to the boundary. And we model the planet Earth with a typical density and pressure profile. And if after modeling, if you interact it, we'll get the video that I have already shown. So let's come to a snapshot of that video, which is basically what we call a steady magnetosphere, or a steady state dynamics of Earth's magnetic field. Here, this is called, I'll give you certain nomenclature so that you understand. This is called a bow shock, the boundary region, which basically dictates the supersonic and subsonic solar wind. The boundary on one side, you'll see get supersonic solar wind. By supersonic, I mean the plasma, the speed of sound is more than the local plasma speed. By subsonic, I mean the speed of sound is less than the local plasma speed. And bow shock is the boundary. It usually forms when a supersonic flow hits an obstacle. Then we see this is another boundary, which is I drawn with a red line. We call it a magnetosphere. A magnetosphere is a pressure balance between incoming solar wind and Earth's magnetic field. Earth's magnetic field also exhibits a magnetic pressure, and these two pressure balance creates a magnetosphere. And the in-between region between bow shock and magnetosphere, we call it magnetosheath. At the behind the night side, what we see is called a magnetotail. We call the pole region as polar caps. Caps because it's open, it connects the Earth's magnetic field to the solar wind. And this cross region is the reconnection region. For this particular scenario, we have a day-side reconnection region and a magnetotail reconnection region, where the opposite direction magnetic field cancels each out, plasma gets energized, and because of this plasma energy, the plasma got energy, the particles follow this magnetic loop, do a helical motion, and okay. So now come to a fundamental question. Why are we using 3D modeling? Because like, why do we need a 3D model which is computationally so expensive? I already showed you the huge computational domain. We have to solve a coupled equation in all 3D. So I'll show you two figures, and I believe with these two images, you yourself will understand why we need 3D model. So on your left, It's a very like classic story that we have heard in our childhood. That we have asked blindfolded man, those who never seen an elephant before, to describe an elephant. And we have sent several spacecraft to an enormous volume of magnetosphere to understand the magnetosphere. Now, the both will give you localized information. But, and when you want to connect those localized information, it's not at all easy. That's why we need architectural modeling that describes the global picture. For on your left, the elephant, on your right, the magnetosphere, which is basically impossible with single point observations. So that describes that dictates well why we need 3D modeling. So why we need 3D MHD modeling? Now, as I already told you that if you really want to describe plasma, you can describe it with kinetic theory, where you actually focuses on the plasma particles and its dynamics, or a hybrid model, or a fluid model. Now, as your length scale increases, you tends to describe plasma using fluid models. And here, the dBi length, which basically for a typical star-planet interaction system, the dBi length, which basically characterize the length scale over which the charge particle and electric fields basically interact with each other, is around a few meters. And the gyro radius of proton is around few hundred kilometers. And if you recall, I told you that the grid size that we are considering is 2000 kilometers, which basically means few thousand kilometers. So the length scale that we are dealing with, the magnetohydrodynamic or MHD description of plasma suits better. So that's all in star-planet interaction. We understand how Earth will have a magnetosphere, Earth has a magnetosphere, why we do 3D MHD modeling. Now I have another question to you. This is a simple yes or no answer you'll have to give. You don't have to shout, keep the answer within you. Does the solar wind forcing of Mars and Venus's magnetosphere look the same as Earth's magnetosphere? You have again 5 seconds. What do you think? Yes or no? Now, I won't give you a direct answer. Rather, I'll show you some figures. The first one that you can see on your left is the day side reconnection region, which is denoted with X1, for a planet which has a magnetic field 10% of Earth. The middle one, now you see the reconnection region has moved towards the planet, and the planet has a magnetic field, which is written here, which is 1% of Earth. And the last one, where the planet doesn't have a magnetic field, and you don't see a reconnection region on the day side. And we call it an imposed magnetosphere. So for Mars and Venus, we mostly see imposed magnetosphere because they don't pose a global magnetic field as a planet. And how the dynamics look like for an imposed magnetospheric, you see, this is how the dynamics look like. Okay, you see, this is an imposed magnetosphere. Now, let me tell you an interesting story that scientists has found that Mars earlier had a magnetic, which later somehow the dynamo got switched off and Mars lost its magnetic field. And because of that, Mars lost its atmosphere also. So the magnetic property of a planet helps in holding the atmosphere other than the gravity. Okay, the gravity is not the solely responsible for holding the atmosphere for a planet. Now let's move on. Let's move on to the second chapter, which is to study space weather. Now, there is a trivia. If you can see the video, the trivia is that the strength of the aurora and the latitude of the aurora tells you about the strength of a geomagnetic storm. This is a trivia. This particular video was taken by Aditi. Aditi was a BSMS student here at CSE IISA Kolkata. Now let's move to the very first question again, and I'm not going to answer it because by now you all know what is space weather. Space weather is basically, again, I am basically answering it. So time varying condition of the space surroundings the Earth influenced by the solar magnetic activities. So if I break it, let's say I want to describe space weather to a class 5 student. We have weather, right? Which is influenced by the atmospheric condition and the rotation of Earth. And that in that weather, we see summer, we see winter, we see storm, we see calmness. Similarly, the space surrounded by Earth also see changes, time varying changes, and that change is driven by solar magnetic activities, where the solar wind drives the quiet time. So as of in the previous section, when I discuss about the solar wind driven quiet time, solar wind driven magnetosphere, it is basically a quiet time. Now if you are really naive enough, think about the scenario. A solar wind which is coming like with a velocity of 400 km per second. This is basically Delhi to Nainital in 1 second. With that velocity, the solar wind is coming and hitting Earth, and I am calling it a quiet time. So what would be the storm time? I very much guess you know by now is the coronal mass ejection. Now I'm not going to describe coronal mass ejection again for you, and I know you basically know what are the pictures are saying, that you can see that there's an eruption, there are spectrograph images. But when a coronal mass ejections come and reach Earth, you see this kind of a typical structure that you can see on your left side. It has a shock region, then it has a sheath region, and a typical flux rope region, which has a twisted magnetic field. If you have followed Pratik's talk well, by now you know this. And this is a video from Enlil, which shows that how a CME basically, a sun throws a CME into the heliosphere. Now the question arises is, can we utilize the same 3D MHD can you utilize the same 3D MHD simulation to understand the storm time space weather? The answer is obviously yes. Otherwise, why I'm talking? And for that, we need a different module, which is SESI storm interaction module. Now, the basic thing that we need here is we have to model the CME near Earth, because you already know that whatever we are doing is focused on near the planet. It's focusing on near the planet. So we assume this typical scenario. On your left, you can see that a flux rope is emerging, which is expanding. When it comes near Earth, if you really see, you can think it of a typical cylindrical structure with a length scale. And then you model the cylindrical structure with various flux rope models. I particularly use Goldwheel. We can even use Landquist also, which Pratik was already talking about. And then we consider the flux rope is not expanding, just to make our life easy. While crossing the Earth, the flux rope was not basically expanding, and then we simulate the situation. So if I draw an artistic impression for you, this is how a flux rope comes from sun, and this is the computational domain. If I rotate the computational domain in 3D, the computational domain looks like this, and this is the flux, and the flux rope is leaving the computational domain. So this is the very basic principle in which the storm interaction module works. Now I'll get into a bit more details about modeling the flux rope. We use, as I already told you, Goldwheel type flux rope, where this typical BR, B5, BZ are the description of magnetic field of the flux rope structure, which you can think of coaxial magnetic cylinders. Now, intuitively, you can see that this typical structure is symmetric about the axis of the flux rope because it's a function of R only. However, when we see a in situ measurement, this is from wind spacecraft, and the blue region in between dictates a flux rope, you see the magnetic field is not symmetric, whereas the red line, which is the modeled one, is a symmetry, because we are modeling with a symmetric flux rope structure, whereas the observation is not symmetric. Why the observation is not symmetric? Because again, what we see at 1 AU is not the intact flux rope. While coming, either the leading edge or the trailing edge of the flux rope has either eroded or interacted because it was dragged by the solar wind while traveling into the heliosphere. So we tried to model an eroded flux rope. How? We see that if we consider this as the symmetric structure, the blue dashed line, and then model it in a way that this typical initial part we consider as eroded away of the symmetric structure, and the green patch region thing, which is what remained intact and unaltered and reach Earth. In that way, we can consider the more realistic version of a flux rope near Earth. And as we interact this flux rope again with the dipolar magnetic field of Earth, we see something like this. So this is the initial dipolar magnetic field. Initially, it will start with a solar wind because solar wind is omnipresent. So solar wind will come. See, it will create the known magnetosphere, which is a day-side magnetopause, magnetotail, current region, the polar caps, and now the CME comes. Okay, now I usually describe CME in a funny manner. The manner is, if the solar wind creates a sleepy kind of tired magnetosphere which doesn't want to change its shape, the CME comes and basically give a slap to it. Okay, that's what it is. It's a funny way, but that's what it is. If you look at it again, it will basically tell you that. Let me play the video again. Why it's not giving me the option? Oh, it's not giving me the option here. Oh, I'm sorry. It's not giving me the option to replay it again. Yeah. Again, let's see that. This is the solar wind. Everything is steady. Nothing is moving. The current is steady. The day-side magnetosphere is steady. We have a magnetotail region, calm, quiet, cool, about to sleep. Now the slap. Okay. Now let's move forward. Now let's look at the current structure, because we have different current structure around Earth. Now here is a catch. When I am doing a MHD simulation, the current I am talking about is the induced current. J is equals to, J is proportional to curl of B. This is not a particle current where a particle or a charged particle is moving and we are getting current out of it. This current is a result of topology, and this we can only talk about this induced current because we are completely considering plasma as a fluid. So let's play this. Okay, why this video is not playing? Yeah, let's look at this video. As the CME comes, how the current basically evolves. You see, the current becomes strong in the day side and then the magnetotail side. If you look from the North Pole, the current becomes strong and makes a circular-like structure around the Earth. Okay. Now I'll come to the video later again. But let's move to another interesting science that we get. What you are looking at is the cross-section of current in the magnetotail region. I guess you can recall what is a magnetotail. I just took a cross-section of the magnetotail. On your left side, what you see is the current region. On your right side, what you see is the plasma region that was observed by Geotel in 1998. You see, more or less, the plasma structure and the current structure very well like complements each other. And now if I play this video, you see there's a typical dance of the magnetotail from the left to the right. Now, why is this happening? If you really notice, I'll come to that, but the magnetic field of a flux rope is twisted. Because of the twist, the magnetotail itself has a rotation because the magnetosphere tries to get itself shaped with respect to the incoming plasma. And since the incoming plasma has a magnetic field which is basically changing its orientation within a short duration of time, the magnetotail region also gets a twisted. That's why we, in the cross section, we see a left to right movement. Again, see, there's a left to right movement. And this is not all. I already told you about the magnetopause bounded. Sorry. So in the day side, we have a typical magnetopause boundary and a standoff distance, and we think that since we have a magnetic field, we can stop the incoming solar wind at least 6 to 10 RE, where RE is radius of Earth, kilometer 6 to 10 RE away from us. On your right, you see the typical magnetopause structure for a quiet time scenario. The dark region is the solar wind, and the white region is the Earth's magnetic field. Because of their pressure balance, we see a boundary region. And now if I play this video, you see how CME basically pushes the boundary. Initially, again, let me play this video again. So initially it pushes the magnetopause boundary towards the planet. So I'll come to this. It has a nice, why, because we see this, it has a nice connection with the ring current. I'll come to that. So when we calculate the standoff distance, which is basically distance from Earth to the nose of the magnetopause, we see that the standoff distance is inversely proportional to the dynamic pressure power n. So the n has a typical value of 6 if you calculate it theoretically. If various simulation has found it between 5.8 to 7 almost 8, and when we estimate it using Stormy, we get at a value within 6 to 8. So basically, this tells us that whatever we are getting with Stormy is relying well with the other contemporaries. Now let's come to a interesting scientific phenomena that's happening in the atmosphere, which is Joule heating. Usually we study Joule heating when we study electrical current, but let me tell you that in Earth's atmosphere you also see Joule heating, where in the auroral region we have the open magnetic field lines, and as I already told you, the magnetic field lines, the particles follow the magnetic field lines and enters into the Earth following the polar region. When charged particle enters the Earth's magnetic field, it collides with the neutral atmosphere, and because of that collision, it dissipates energy in terms of Joule heating, because they are charged particles. This is in a very fundamental way. I mean, it's not as simple as I just told you, but it's the very fundamental way. Now, when this Joule heating arises and then it dissipates among the whole atmosphere, the atmosphere basically expands. Now, this is a counterintuitive idea. Think about, you have a gas and you are giving it thermal energy in terms of Joule heating. So you will see the gas will expand. As a result, the density of the gas will coming down if you allow the volume to expand. Very basic thermodynamic idea. So for Earth also, if the atmosphere is heated up by the Joule heating, we should see that the atmospheric density is coming down. But that's not the case. Why? Because let's say you have a spacecraft at 100-kilometer altitude. So somewhere here. So earlier, it was facing a density, let's say for example, two proton per semi-cube. And now, since the atmosphere has expanded, thicker atmosphere from lower altitude has come to 100-kilometer. And the low density atmosphere from 100-kilometer has risen up. So the same satellite at 100-kilometer will now face more dense plasma, more dense atmosphere, which will enhance its satellite drag. I hope I made the satellite drag clear to you all. Now, why I am talking about satellite drag and Joule heating too much? Because Joule heating leads to a typical equation which says that the power per unit volume is proportional to the J square. The proportionality constant is here the resistivity, and in the ionosphere, the resistivity is not isotropic. So we'll just try to understand Joule heating in terms of J square. So we take an average of J square over a geocentric sphere of 10 RE, and this is a typical J square value during an event of February 2022. And when we compare it with a Joule heating value, which was taken from our actual Joule heating model, you see that the Joule heating, which is in gigawatt, whereas we are getting J square in nanoampere per meter square whole square, they are matching in terms of peak to peak. So qualitatively, even we can estimate how much Joule heating enhancement we can see during storm time space weather. Now here is a meme. I will really want to ask you if you can correlate this guy with the background image. I want the volunteer there to give someone a mic who can answer this. Anyone?
February 3 Starlink disaster.
Yes, thank you. I mean, it was very obvious. It's almost a year now. Still, I really wanted to know that you guys, how much you guys are taking information. I mean, how much updated you are. So the Starlink event happened during somewhere here. The pointer is the Starlink launched 49 satellites during that time. Out of 49, 38 satellites got lost because the atmosphere was perturbed already, and later it was perturbed again. So let's move to the important question after Starlink, that why it is important to study and predict space weather. And Starlink massacre was the biggest example. Till I'll show you certain screenshots. So these are all the papers related to space weather massacres that happened in recent past. We get humans, the effect can be on human space exploration, on satellite communication, on high frequency radio communication, on electric power transmission, on satellite drag, the poor Elon Musk, navigation, and of course we see good, nice eye soothing aurora. That's a different thing. So the question is, can we again utilize the 3D MHD simulation for predicting space weather? Why not? We have storm interaction modeling. This is again cliche, but I can't help it. So how can we quantify space weather? Like, for example, let's say I want to measure earthquake. We need to have a Richter scale, basically, that quantifies earthquake, the level of earthquake. So to quantify space weather, before that, let's understand a few terms. Geoeffectiveness, geoeffectivity. So geoeffective is basically capability of causing a geomagnetic disturbance of a CME or CIR, what is incoming. And geomagnetic index is the quantification of geoeffectiveness. And like Richter scale for earthquake, we have DST index, we have symmetric H index, we have KP index, AP index, AE index, PC index, symmetric H index, asymmetric H index, asymmetric D index, symmetric D index, and many more. Okay. So these typical indices look at certain phenomena and gives us an understanding of when a storm is going to come. So I will focus on DST and symmetric H index, because it has a keen connection with the ring current. What is ring current? Now, within the Earth's magnetosphere, we have trapped protons. The protons comes from the ionospheric region as well as from the solar wind region. And all these trapped protons basically move roughly a circular path around the magnetic equator, and it is guided by the Earth's magnetic field lines. So you can see here, this red line shows the typical orientation of a ring current in Earth's magnetosphere. There are other currents like magnetopause current, neutral sheath current, tail current, field aligned current, which I was talking about while talking about Joule heating. Now, the ring current has a beauty that the direction of flow of the current is such that it creates a magnetic field opposite to Earth, basically Lenz's law. Now, we have various ground-based observatories, and these typical 11 are near the magnetic equator. You will be happy to know that one is in Alibag, Mumbai, which also a part of this ground-based magnetometer network. And from this magnetometer network, DST is calculated using 4 observatories, and symmetric H is calculated using 11 observatories. Actually 6, but 11 observatories are used. And these indices measure the deviation of the horizontal component of the geomagnetic field, which means let's chronologically connect this in a way that there is a storm in the magnetosphere. Because of the storm, the magnetopause moved, more particles came into Earth within the Earth's magnetosphere, so more entrapped ions. Because of more entrapped ions, we see high ring current. Because of high ring current, the Earth's magnetic field is now getting weak. As the Earth's magnetic field is getting weak, we see that the deviation will be higher, so the index will be negative. And whenever we see a negative index, we say there is a geomagnetic storm. So this is the typical chronology between enhancement of ring current and the DST and symmetric H measuring a geomagnetic storm. Now, let's come back to our simulation. So we have this typical, on your left hand side, this is a cross section of the equator from our simulation. The background is showing you the current density in terms the amplitude of current density vector in terms of color, and the arrows are the orientation of the current density J. Now, pardon me if you can't see it because of the background color. So I'm really sorry, because the background color is not it's very dark and the arrows are on black, so it's really hard to distinguish. But if I play the video, you'll see that this is how the current changes. Now, the interesting fact was, when we basically matched this current with the ring current, we saw that this current has a typical orientation of the ring current. See the magnetopause current, if you look from the North Pole, the magnetopause current are anti-clockwise. See this is the magnetopause current, which is anti-clockwise. The ring current is clockwise. See here, the current moves in a clockwise direction. Now, this is not ring current, as I already told you, because we are not utilizing the particle description. We are using fluid description. This current density comes from the topology. But the topology has a beauty that this current matches the ring current. So we thought, since it matches the ring current, why can't we utilize the Biot-Savart law and calculate the magnetic field deviated by this typical current? So what we did was, and similarly like the ground-based magnetometers, in our computational domain, we choose certain grid points as our virtual observatory. And then we consider the current during quiet time, which is during the solar wind time, will be the baseline. So the current that we'll get during the solar wind will lead to a zero index. And then the CME will come and we'll see how much the magnetic field decreases from that zero index. And we call this typical index that we simulate the stormy index, storm interaction index, which is a proxy to DST or symmetric edge. And then we simulate two events. This one was the extreme event that Earth has faced in last 3 decades. It has a DST around 423 nanotesla. It has a magnetic field, central magnetic field around -50 nanotesla. And we simulate another moderate event to understand the length scale, which was a moderate event around 100 nanotesla. Now, if I plot the storm index, which is in blue, and the DST and symmetric edge index, which is in the black solid and dashed line, you see this is the comparison. Okay. Now you see a span in the blue because we have 14 observatories and we have to get a standard deviation from all the values from all the observatories. But this is a very much intriguing result because I'm again pointing out that this is we are getting from a plasma simulation. Why I'm pointing out again and again, I'll come to that later. But let's try to understand that this is not a fluke. Let's connect the current that we were getting with the DST value. So now you see on this slide, when the DST is maximum, the currents are also maximum. As the DST is performing well again, as the DST is going near zero again, the current is reducing again. Similarly, for the moderate event, again, if I play, you see initially when the storm index was positive, we don't see strong current. As soon as you see the storm index will go to negative, we'll see the current is increasing and enhancing. This is awesome. Now, let's do a quantitative analysis because me saying awesome doesn't help. We get a DST around 422 nanotesla. We get a storm index, which is much more higher, but of the same order. So if you see in order wise, we are matching the extremities. Not only that, if you want to match how the linearity between the coefficients are going, you see the linearity is pretty high, more than 0.8, which dictates the storm index perform really well as a proxy of DST. So with that, let's move to the question, why we are saying proxy? I mean, why can't say that the storm index is basically the DST and symmetric index? Because we have not used the particle or ring current definition within our simulation. But as I already showed, that it performs really well as a proxy and it has a typical prediction skill. That's what we are talking about, predicting space weather. So can we predict space weather in real time? Like if I see a CME and can we just get to know what the DST will be? Sorry, but no. Why? Because with our current computation power, it takes 2 days to run a complete simulation, whereas it takes only 60 minutes for a CME to reach Earth from L1 point from where we are getting the CME data. But this is not the end, because let's think about the global scenario. We have a models, we have a sun, we have the spacecraft at L1, we have Earth. Now, typical CME takes at least 2 days to come to Earth, whereas 45 minutes to 50 minutes to come to Earth from L1 point. Now, you probably know that we have a machine learning based flare prediction algorithm, which basically predicts flare in SESI. We also have a cloud prediction model, which basically predicts how the flux rope will look like at 1 AU based on the near sun observation. And it's a semi-analytical model. So now we have a model that as soon as there is a CME, it will tell us that the flux rope is going to look like at 1 AU. Then we can utilize storming and we can get a DST value. So this particular project is currently ongoing. We believe that we have a gut feeling that very soon we are going to predict the geoeffectiveness of a CME as soon as it erupts from the sun. So let's point out the importance of storming and why I was talking about this ring current, fluid dynamics, fluid integration, not particle integration too much. See, on your left, you see certain empirical or semi-empirical modeling that already gives you the prediction of DST. But these models, how they predict DST, they use semi-empirical understanding. For example, let's say have a statistical data set. You perform a statistical analysis and then see that DST varies on BZ or velocity with some parameters. And then you use that empirical modeling to predict DST. It's already there. On your right-hand side, you see certain 3D magnetospheric simulation modeling, which is SWMF, Open, GGCM, CMIT. What they do, they couple magnetohydrodynamic model with the ionospheric model, with the electrodynamic solver, with the inner magnetohydrodynamic model, with a comprehensive link current model, and makes the computation highly expensive. Because of this super expensive computation, you cannot basically utilize this typical 3D magnetospheric simulation for predicting DST. So what we have on one side, which is semi-empirical or empirical modeling that can predict DST very well, but this will just give you a DST value. It won't tell you that how the magnetosphere is going to look like, how the current is going to look like. On the right-hand side, we have 3D modeling, which is going to tell you how the magnetosphere is going to look like, but they are so much computationally expensive that you practically can't use them for prediction purpose. And here comes storming, which is trying to bridge these two paradigms. Okay, so this is basically the importance of storming, which is again I have written. I'm not going to read it out because I have discussed this plenty of times. Now, let's come back. Let's come to the third part, to study planetary dynamics, and from that, to understand the exoplanetary dynamics. So, let's think about a hypothetical stellar body system where the planet has a magnetic field of 1/10 times, 0.1 times of Earth. Whereas the typical stellar wind near the planet is 10 times of what we get at Earth. Now, if we simulate such a scenario, what you are going to see is a nice wing-like structure. Okay. This is called L1 wing, which is very common if you really study exoplanetary magnetosphere. Because you expect to see L1 wing in certain cases where your planet and stellar wind has typical values. We simulated this in SESI to understand how planetary magnetosphere and exoplanetary magnetosphere, to broaden our understanding from Earth to Mars or Venus to exoplanet. There's another interesting result that I want to share with you is related to the mass loss rate. Now, as I was talking about that the solar wind will come, hit the Earth's magnetosphere and go away, it will advect some mass from the planet. If the planet has an intrinsic magnetic field, it will try to protect. If it doesn't, then like Mars, it can't protect. Now, here is a typical case of the mass loss rate if you plot it with various planetary magnetic field by wind magnetic field ratio. And this study typically says that the mass loss rate has a pattern. So if your planetary magnetic field and the stellar wind magnetic field that the planet is facing has a typical ratio, the mass loss rate will depend on that. Not just the planet has a magnetic field won't help, not just the stellar wind is very strong won't help. The ratio of them is basically drives the mass loss rate structure. So with that, I'll end here with all my discussion, but I'll come back to this animation. And I want you to answer what is scientifically wrong in this animation. Again, I'll ask a volunteer there if he or she can give you the mic, and if you can try. I'll play this for a minute to look at it very carefully, because this has nothing to do with solar physics. This has a very keen, you have to have a keen understanding of astronomy. Anyone? You can try. Like, I'm not there, I'm not going to kill you. Anyone? Random guess? Except for the length scale. Okay, so tell me how many full moon you see in a year, or how many new moon you see in a year. Anyone?
Around 13.
Around 13 is correct, but not exactly 13. So I'll not this thing the suspense. Let me answer it. So because of the 27-day synodic period of the moon, we see 13.5 new moon or 13.5 full moon in a year. But in this particular simulation, if you calculate, it's exactly 30. Because since it's a GIF and I have to create a loop, I created it in a way that the moon rotates exactly 13 full rotation in a year. That's a typical scientific wrong description in this animation. But since we're talking about moon, what about the magnetosphere of the moon? From this animation, one thing is clear, that out of the 27 days that I'm talking, moon spent the most of the time facing the solar wind. Let me tell you that it spends roughly 6 days on the tail region of the earth, and the other 21 days facing the solar wind. So let's think about this. When the moon is facing the solar wind, we have already seen that since moon doesn't have a global magnetic field, we'll see a magnetosphere which is going to look like this, right? But what will happen when the moon is in the magnetotail and is not facing the solar wind? I'm going to leave this as an open question to you. I want you guys to think about it based on all the thing that I have discussed with you. Try to intuitively understand what is going to happen around the moon when it's in the magnetotail, not facing the solar wind. With that, this is the list of publications that I have discussed in the whole talk. You can refer to that. You can email me if you have any queries or anything related to that. I have given my whole address. If you want to come visit me, you can come to Sesi, but for that you have to write to Dibendu first. And that's all. A big thank you to you all.
All right. Thank you, Souvik. So now we can have questions.
So we talked about mass loss due to solar wind, that we lose mass to the solar wind of our atmosphere. Is there a chance that we'll gain mass from the solar wind if the solar wind is slow enough? And if so, how slow must the solar wind be to gain mass from it?
See, we always gain mass from solar wind. When I was talking about ring current, the ring current enhances because the solar wind particles enters the Earth's magnetosphere. It may not come to as low latitude as our like 100 kilometer or 50 kilometer or 200 kilometer, but within the magnetosphere, we always gain mass from the solar wind, as well as we always lose mass to the solar wind. This is a you, I mean, continuous process. I think the term is ubiquitous process. And if you ask me the typical value of the solar wind, I can give you an intuitive answer. Let's say if you have a very low planetary magnetic field, and if you have a high stellar wind magnetic field, there's a high chance that you will get the particles from stellar wind, and as well as you will lose it also, because nothing is there to hold it.
Thank you, sir.
Sir, what is the effect on Earth horizontal magnetic field during this geomagnetic activity?
I can't hear you properly. Can you just repeat?
Hello?
Huh.
Sir, what is the effect on the Earth horizontal magnetic field during this geomagnetic activity?
So during geomagnetic activity, horizontal magnetic field decreases, because as I told you, as the ring current enhances, it has the ring current flows in a way that it tries to minimize the Earth's magnetic field, the Lenge's law. Now, when there is a solar storm, the ring current enhances. At ring current enhances, the Earth's magnetic field becomes lower as we see it from the horizontal magnetic field based on the ground-based observatories. So, to answer your question, we'll see that the horizontal magnetic field will decrease.
Okay, and what is the measure of that symmetric edge index? I didn't understand that.
So, symmetric edge index and DST index are basically twin in terms of the typical physics or typical technology calculating the both index are same based on the ring current and the decrease of the horizontal magnetic field. However, DST comes once in an hour, so the frequency of data cadency is once in an hour, whereas symmetric edge is like once in a minute. So symmetric edge you can treat it as a high resolution DST. Although, like me as a modeler can say that if you ask a space weather guy, he'll kill me if I say DST is a high resolution, symmetric edge is a high resolution DST. But on a broader perspective, if I again, okay, let me share. Is my screen visible to you? I think yes.
Yes,
So,
it is still.
So let me write the plot of DST. Yeah. Look at the line, which is solid line, which basically shows symmetric edge. The dashed line shows the DST. So it's basically a smoothened symmetric edge is nothing but a DST. But you cannot say that because the calculation has it's not exactly the same. But on a broader perspective, you can consider that.
Okay, thank you. All right.
Sir, during storm in geotail, the PSBL and the LLBL activity, can you explain?
Sorry.
During this geomagnetic storm, the PSBL and LLBL at a geotail.
Yes.
Can you explain it?
So by PSBL, are you like referring to the plasma boundaries?
Yes.
Define PSBL for me. I'm not getting it.
This one.
So wait, let me minimize this. The PSBL is, PS is called the plasma sheet. The plasma sheet creates because of the reconnection. So whenever you have a magnetic field, which is basically one direction on the top, other direction on the bottom, because of that you see a current sheet. That's the PS, which is basically the plasma sheet. Above the plasma sheet and below the plasma sheet, you see the lobe region. And let me remind you, the L1 wing that you see is this lobe region only, which is basically subalveolic region. So this is the lobe region. The PSBL and the this is basically plasma sheet boundary layer. You will see a plasma sheet boundary layer. So let's say you are sitting on a spacecraft, you are basically going top to bottom. You will see that the plasma sheet has a boundary layer. That's has a dark color here, and they have given it a name, that PSBL, the boundary layer of the plasma sheet. You'll have a lower boundary layer and upper boundary layer. And the dynamics of within the boundary layer will change based on the orientation of the Earth's magnetic field. Because if I again take you to this video, this is why I made this video. Wait. If I again take you to this video, you see the magnetic field is more towards sun during June. You'll see the magnetic field, north pole of the the north polar region, which is basically the south pole of the magnetic field, will be away from the sun during December. This typical orientation has a say on the geomagnetic field, which I have not discussed here. So the magnetic orientation also has a say on how the plasma layer, the plasma sheath, how the magnetofield dynamics is going to happen.
All right, more questions? Okay, if not, let's thank Souvik again. Thank you very much, Souvik.
Thank you guys for allowing me to give a talk. I don't know they understood or not, but I hope they enjoyed.
Sure, I'm sure they enjoyed. Thank you very much, Souvik. Some of the TA forms have not been submitted by some people. If you want the reimbursements, you have to submit it today to Balveer or I don't remember the other name. Sorry, Sanmoy. Yes. So please submit. Whoever did not submit, please submit the TA forms if you want the reimbursements. So, and then we can take a break of 10 minutes and then move to lunch at around 1 o'clock. All right. We will see you back again in the afternoon. We have a public lecture in the afternoon. Don't forget.